Anyway, we are starting section 3, which is exponential functions. So basically, an exponential function is designed to show rapid growth or decay, right? Something that is growing very, very fast or something that is decaying very, very fast, all right? It's growing at an exponential rate usually, all right? So let me skip down to just the definition of an exponential function, and then we'll come back up and start taking the notes from the top. So by definition, an exponential function is a function of this form. F of x equals c times a to the power of x, all right? Where a is a positive real number. So guys, just by definition, that's extremely important. By definition, an exponential function, the base a, yes, there will, Michael, as always, yep. The base a has to be a positive number. By definition, the base of an exponential function is not allowed to be a negative number. And we'll get into more of why in a little bit, all right? Where a is bigger than 0 and a is not 0, and c is not 0 because 0 times something wouldn't exist. We don't want the constant in front to be 0. So basically, in a nutshell, an exponential function is a function where the variable is the exponent or part of the exponent. Normally, when we've worked with expressions or equations so far, the variable has been the base, like x squared, right? Well, now we're going to start working with functions where the variable is part of the exponent, like 2 to the x. So we're going to be working very heavily, obviously, with exponents when we work with exponential functions. So if we're going to be working with exponents, the book wants you to realize something, that normally the way we work with exponents, all of our exponent rules and properties, they apply to real rational number exponents. Rational numbers are numbers that can be or already are written as a fraction. Normally, those rules for exponents didn't apply to irrational exponents, like a number like the square root of 2. So they just want you to realize that if you take an irrational number, like the square root of 2, an irrational number is a non-ending, non-repeating decimal. It's a very, very ugly number. So the square root of 2 just keeps on going forever and ever and ever and ever. So if you use a number like that as an exponent, that can be difficult because normally in order to use it, you'd have to round it at some point. And normally when you round, that loses accuracy or a correct answer, if you will. Like your equation could 2 equals 2 and ends up being 2 equals 1.19999 or something like that. All right? So they're trying to show you that if you use an irrational exponent, right, like 2 to the square root of 2, you get 2.665144114. And this will keep on going. I had to stop. It said to round to 8 decimal places. Well, if you take the square root of 2 and you round it to just 1.14 or 4142, the answer isn't all that different. If I round the square root of 2 a little bit more to 1.414, the answer is still not that different than when I use the actual square root of 2. So as I take the square root of 2 and I round him a little bit more each time as my exponent, the original answer and then the rounded answer, they're not exactly that far off from each other. So they're trying to show you that if we have to round an irrational number, our exponent answer is not all that different. So they're trying to let you know that the exponent rules are going to be allowed to apply to irrational exponents as well. So if we have to use an irrational number as an exponent, we can still use our laws of exponents on it. Because normally in the past, you would only have used your laws of exponents on a rational exponent, not an irrational exponent. But there's going to come a time as math gets more difficult to use irrational exponents. So they're just trying to show you that the answer isn't that far off. So now they're going to let you apply the laws of rational exponents to irrational exponents too. So let's just review some exponent rules really quick. We know that in a multiplying problem and the base is the same, we will add our exponents. When it's a power raised to another power, we will multiply our exponents. When we have multiplication raised to a power, we can distribute that power. We know, though, that when it's adding and subtracting in between, we would never distribute an exponent over adding and subtracting. That's a foil in disguise. We know that anything, a base of 1 raised to any exponent is always 1. I know this is a little hard to read. I apologize for the blurriness. A to the negative s, a negative exponent is fixed by flipping it. That's 1 over a to the s. And then anything raised to the power of 0 is 1. So these are all of our exponent rules. They're just saying that now we're going to be able to use these exponent rules when the exponent is an irrational number, not just a rational number. And then I added this one over here, the subtraction. When you're dividing, you subtract and you put it back wherever the bigger exponent was. So if s is bigger than t, we'd put it back on the top. Okay, so that is our exponent rules that we'll be able to use when we're working with these exponential functions, these functions that are designed to show this rapid growth, something that is constantly getting bigger and bigger and bigger, or smaller and smaller and smaller, proportionate to time. All right, so an introduction to an exponential growth. Let's look at this. So it says, suppose you are given $10 and you are told that each day you show up to class, the amount you're given doubles. Well, wouldn't that be nice? Fill in the chart below. Well, guys, obviously we could fill in this chart very, very quickly. Every single day, the amount of money you had previous doubles. So on day 0, you start with $10. On day 1, that amount would double and we would have 20 bucks. On day 2, that amount would double and I'd have 40 bucks just for coming to class. On day 3, it would double, I'd have 80 bucks, and then it would double 160, 320, 640, 1280, and then 2560, right? And we could obviously just keep on going as each day goes on and on and on. All right, so obviously that's exponential growth. It's something that is growing at an exponential rate. In a matter of 8 days, you went from having $10 to $2,560. That is something that is growing at an exponential rate. So yes, it's very easy to work with like this, but if we want to think of it as more of, let's put this from an exponential function point of view, how could you come up with a function to show this? Well, think about it this. On day 0, you had 10 bucks, right? Okay. On day 1, you're going to take that $10 and you're going to double it. So you're going to times it by 2. We get 20 bucks, right? Okay. So notice on day 1, you're taking 10 and you're timesing it by 2 to a power of 1. Day 1, power of 1. All right, day 2. You're going to take your 10 times 2 from the previous day, right? And you're going to double it. So in reality, you're taking 10 and you're timesing it by 2 times 2, which is 2 squared, which is going to equal you your 40 bucks. So you think about it, day 2, you're taking your $10 and you're timesing it by 2 squared. Day 2, power of 2. On day 3, you would take the previous amount, your 10 times 2 squared, and you would double it. So now you're really taking 10 and you're timesing it by 2 squared times 2, that's 2 to the 3rd, which is your 80 bucks. So on day 3, you're taking your $10 and you're timesing it by 2 to the 3rd. Day 3, power of 3. On day 4, you're going to take your previous amount, 10 times 2 to the 3rd, and you're going to double it and you're going to times it by 2. So you're taking your $10 and you're timesing it by 2 to the 4th. And that's going to be your $160. So you can see the relation here between the day and the power. On day 4, I'm taking my $10 and I'm timesing it by 2 to a power of 4, where we could then use this relationship on day X. What would you be doing to your money? On day X, you would be taking your $10 and you would be timesing it by 2 to the power of X. And you have just written an exponential function to model this data. All right, so we could say f of x equals 10 times 2 to the x. And there is an exponential function of the form c times a to the x, like I said, that is modeling this data. So this is how exponential functions are going to work. We're going to have an unknown value represented by that exponent, all right? And you have a base and you have a constant. All right, so that's exponential growth, something that is growing very, very, very fast. Let's go back to the definition. So an exponential function is a function of this form, where a, the base, has to be a positive number, and the variable is part of that exponent, all right? What is the domain of an exponential function? What should I be allowed to plug in to represent that variable? Well, guys, the beauty of an exponential function, the way it is designed to show this growth or this decay, is the domain should be all real numbers. And that is why the base is not supposed to be negative. We want the domain to be all real numbers. Over an infinite amount of time, we should be able to find this growth or this decay rate. I don't want to exclude x values from the domain. All right, the base A is called the growth factor. If you notice, the base of this exponential function we wrote was 2. And what were we timesing our money by? By 2. It was doubling. So the base is what you are multiplying your initial value by. You're doubling it. So your growth factor is 2. So if I was going to times my money by 3, if I was going to triple it each day, my base of the exponential function would have been 3. If my money was going to be cut in half each day, the base of this exponential function would have been 1/2. It's your growth factor. It's what you're multiplying your money by. Okay? And because f of 0 equals c times a to the 0, well, a to the 0 is 1. 1 times c is c. Since f of 0 will always equal c, that initial constant, then we call c the initial value. So on day 0, I started with 10 bucks. $10 was my initial start rate, my start money. Okay? All right. So there's a couple things to take note of when you're working with an exponential function. If c is equal to 1, then f of x equals a to the x. So if your constant in front of your function is 1, then you're just left with the a to the x part, which is the simplest form of an exponential function. When there's no constant, it's just a base raised to some power. That's the simplest form of an exponential function when c is equal to 1. The base is not allowed to equal 1 because if the base of your exponential function was 1, 1 to any power is always going to be 1. So it wouldn't be showing any growth. So that's not an exponential function if it's not showing any growth, any increasing, or any decreasing. So the base can't be 1 because it doesn't show any difference. All right? By definition, the base is never a negative number. Many x values would have to be excluded from its domain. Guys, if we let the base of an exponential function be a negative number, right? Like y equals negative 2 to the x. The base is negative. If I tried to plug in 1/2, then I would have negative 2 to the 1/2, which is equal to the square root of negative 2. You can't take the square root of a negative number. So now I'd have an undefined output, which means 1/2 would not be in the domain of this function. Or any even root radical wouldn't be in the domain of this function. So there's too many x values you would have to exclude from the domain if we allowed the base to be negative. Also, if the base was allowed to be negative, let's stick with this one. If I plugged in 0, negative 2 to the power of 0 would be what? Negative 2 goes in, 0 goes in, and a 1 comes out. If I plug a 1 in, negative 2 to the first power is negative 2. So 1 goes in, negative 2 comes out. If I plug a 2 in, negative 2 squared is 4 comes out. Guys, do you see this? It's going down and then up. And then I plug in negative 3 and negative 8 would, 3 would go in, negative 8 would come out. Now it's going down. It's not showing this constant growth. It's showing growth, decay, growth, decay. So it's another reason why you wouldn't want the base to be negative. If the base is negative, then you're not going to show this constant increasing in this function or this constant decreasing. It's too much back and forth between increasing and decreasing. So that's why, by definition, the base is not allowed to be negative. It doesn't show what an exponential function is designed to show. All right, so let's put it to a test then. So if that's how an exponential function works, then we want to be able to identify an exponential function from a non-exponential function just by looking at the data. All right, so notice that in the previous exponential function where our money was doubling, f of x equals 10 times 2 to the x. The ratio of consecutive outputs is constant for each 1 unit increase in the input. So if you look at your back-to-back outputs, 10 and 20, 20 to 40, 40 to 80, 160 to 320, 320 to 640. If you look at your back-to-back consecutive outputs, they should show the ratio that is your growth factor if it's an exponential function. There is a constant ratio between consecutive outputs if you are an exponential function, and it should equal the growth factor. All right, so to prove that this is exponential data, we want to prove that this is this constant ratio between the outputs. So you want to compare what it became to what it was. If you compare what it became to what it was, you should see this constant ratio between outputs. So guys, take 10 and 20. Take two consecutive back-to-back outputs. If I compare what it became, 20, to what it was, what's 20 divided by 10? 2, which is my growth factor, that constant ratio of what I was doing to my money, that constant doubling of my money. Take the next back-to-back outputs. All right, 20 and 40. Compare what it became to what it was. 40 over 20. What's 40 divided by 20? 2. There's that constant ratio between outputs. Take your next consecutive outputs. 80 and 40. It became 80, it was 40. What does it divide to? 2. So all of your consecutive outputs in an exponential function will show this constant ratio, this growth factor between outputs. So as long as you can prove that there's an equal ratio between them, you are proving that this is exponential data. So I'm going to keep going. 160 compared to 80, I get my 2 again. 320 compared to 160, I get my 2. 640 compared to 320, I get my 2. 1280 divided by 640, I get my 2. All right, 2560 compared to 1280, I get my 2. So all consecutive outputs have this constant ratio. All right, and that ratio should always be your growth factor, the base of your exponential function. So in a nutshell, they say f of x plus 1 over f of x, right? This is what it was, your original input. This is the next consecutive input, x plus 1. This would be 2. This would be 2 plus 1. This is 3. Always equals that growth factor A. What it became compared to what it was always equals your growth factor. That's how you can look at data and know that it is exponential data. All right, so there's a theorem for an exponential function f of x equals c times a to the x, where a is greater than 0, a positive number, and a is not 1. If x is any real number, then what it became over what it was will always have that ratio a, your growth factor. And then what they end up doing is they end up cross multiplying. If you put a over 1 and you cross multiply, it's just another statement of equality. All right? All right, so now if I prove that f of x plus 1 over f of x, it always equals a, guys. Because if f of x is c times a to the x, well then, plug in x plus 1 for x. F of x plus 1 would be c times a to the x plus 1 over f of x, which is c times a to the x. My c's divide out. I am left with a to the x plus 1 over a to the x. What do I do with my exponents in a division problem? I subtract them. So I would take the big exponent, x plus 1, and I would subtract x. And then my x's cancel. I'm left with a to the first, which is a. So f of x plus 1 over f of x will always equal a. So that's going to be our saving grace. If they ever want you to look at data and ask if it's exponential data or not, this is what you have to prove. You have to prove that consecutive outputs get you that ratio. All right, so that's all we're going to do today. Just because I don't have a lot of time, is I'm just going to give you a couple examples where you're actually going to look and say, is this exponential data? Is it linear data? Or is it neither? All right, so it says, determine whether the given function is linear, exponential, or neither. For those that are linear, find a linear function that models the data. So write a linear function. For those that are exponential, find an exponential function that models the data. All right, so guys, let me give you a little bit of a cheat sheet. If you want to prove an exponential function, right, then you want to prove same growth factor, same ratio. If you want to prove a linear function, we already know how to prove a linear function. A linear function, all your ordered pairs have the same slope. There's a constant rate of change. You want to prove the same slope. All right, now guys, this is important. When you are comparing data for an exponential function, in order to get that ratio, that constant growth factor, you have to compare consecutive back-to-back outputs. So if you notice, all of the data in these charts, X is in a 1 unit increment from -1 to 0 to 1, 2, 3, -1 to 0 to 1, 2, 3. If this was not consecutive outputs, then it's harder to prove that exponential data because by definition, only the consecutive outputs have to have that same ratio equal growth factor, all right? But slope, remember, any 2 points on a line will have the same slope, so that wouldn't matter if we were working with slope. All right, here we go. Let's look at this data, and let's see if this is exponential data, linear data, or neither. So let's go. Let's grab 2 back-to-back outputs. If I'm going to prove an exponential function, I want to prove they have that same ratio. So what it became, 2 over what it was, 5. So right now it looks like back-to-back outputs have a ratio of 2/5. If all back-to-back outputs have this ratio, then we can say it's exponential data. But guys, go grab the next 2. What it became over what it was, -1 over 2. That is definitely not the same growth factor, not the same ratio between consecutive outputs. So we can stop right now, and this is definitely not exponential data. All right, is it linear data? If it's linear data, we want to prove that they have the same slope in between points. The rate of change between your data is the same. So let's find a couple slopes. I'm going to have to do this down here. So slope, I would do 2 minus 5, change in y, over change in x, 0 minus -1. -3 over 1, that's -3. So if I have the same rate of change, the same slope in between points, then I can say this is linear data. I'm going to grab my next 2 points. All right, change in y, -1 minus 2 over 1 minus 0. That's -3 over 1. That's -3. So guys, that's 2 data points that have the same rate of change. So it's looking like it's linear data, not exponential. I'm going to grab my next 2, -4 subtract -1 over 2 minus 1. That's going to be -3 over 1. That's -3 again. And again, I like to check them all because there might be that one set of points that don't have that constant rate of change, and maybe it's not linear either. So I go through all my data. All right, my next 2 would be -7 subtract -4 over 3 minus 2. And that's going to get me -3 over 1, which is -3. So guys, this is linear data. You have the same rate of change in between any pair of points. So now because it's linear, they asked you to write a linear function. Well, what's our go-to equation for a linear function? Good old y equals mx plus b. We already know the slope is -3. I could pick any one of these data points, plug them in for x and y, and solve for my y-intercept, or my y-intercept, when x is 0, y is 2. My y-intercept is 2. So now I can say f of x equals -3 times x plus 2. And I've just written a linear function for this data. I know I feel like I'm rambling, guys. Everybody okay? Let me know. All right, I'm going to try and do one more before the bell cuts me off. Let's look at another set of data. Is this box showing us exponential, or is it showing us linear, or is it showing us nothing? All right, let's go. Again, our outputs are consecutive, so let's grab them. What it became over what it was, 16 over 32 reduces to 1/2. So if I can prove that there is the same growth factor, the same ratio between outputs, I can prove this is exponential data. All right, let's grab the next 2. What it became over what it was, 8 compared to 16 is 1/2. So again, they have that same ratio in between outputs. All right, next ones, 8 and 4. It became 4, it was 8, it reduces to 1/2. So guys, it's looking exponential. It has that equal constant ratio in between outputs, that growth factor. Last ones, it became 2, It was 4. That's 1/2. Guys, this is exponential data. This is definitely showing something that is growing or going down, I should say going down at an exponential rate. All right, so we know this is exponential now. Now we have to write ourselves a function. So what's your go-to formula for an exponential function? F of x equals c times a to the x. Well, remember, this growth factor right here, this ratio, is the base of your exponential. It is a. So we know a equals 1/2. So let's plug that in. So f of x equals c times 1/2, I'm going to put it in parentheses, to the power of x. So now you need C. What was the initial start value of this data? Well, remember, there's two things you could do. You could pick any data point. You could pick 1, 8, plug 1 in for X, 8 in for Y, and you could solve for C. But remember, C always happens when X is 0. When 0 at your initial start time, what was that initial value? So when X is 0, 16 is C. Right? 0C is always that initial value. So when X was 0, Y was 16. So that means C is 16. If they're going to gift you X equals 0 in your data, then you automatically know your C. So now we can say F of X equals 16 was the initial amount they started with, times 1/2 to the power of X. And there is your exponential function. Okay? All right, guys, I apologize. I really feel like I left you hanging. I know I was rambling a little bit. Can I get a thumbs up if you guys are okay? All right. So like I said, right now, they just want you to recognize an exponential function is going to show this exponential growth or this exponential decay. It's going to have a base that is never a negative number. It's never 1 either. All right. And that you can write an exponential function in this form. F of x equals c times a to the x. And if it's exponential, you can prove exponential data by proving this constant growth rate ratio between outputs. So guys, your homework tonight is super, super quick and super, super easy. It's just going to give you a couple definition questions based off of exponential functions, and then it's going to give you a couple of these to try. I'm not going to have time to do this one, but I'll make sure that he's in your written notes, okay? All right, so your homework will be quick and just testing you on this type of information for today. And then tomorrow we'll get into it even more with the graphs of exponential functions. All right, I'm going to double check the attendance and I'll let you guys get out of here.